Everybody out there, welcome. Welcome at this 10th session already of our Getting Technical Live events. Today is the first out of a series of 4, where we are going to talk about milling strategies and milling techniques, something which is very hot for the moment when we talk about machining and what we do with machining. Now, if we talk about milling strategies, first perhaps let's try to be very clear. Advanced milling, is that a strategy or is that a slogan? I would like to ask you here, because if we say advanced milling is a strategy, that means that there is also something then like an unadvanced strategy. And one could ask the question, now face milling, is that an advanced milling strategy or is face milling an unadvanced milling strategy? Advanced means latest developed. So I don't think advanced milling is a strategy. It just means it's one of the later developed approaches to milling. Dynamic milling, is that a strategy or is it a slogan again? Because dynamics is in mechanics the subdomain where we discuss about, where we learn about the interaction between forces acting on a body and the movement of the body. That's dynamics. And a specific chapter in dynamics is vibrations, harmonic movements. So dynamic milling is milling with vibrations. I don't think that's a strategy, that's a problem. So be careful when we talk about things, is what I would like to ask you. My name is Patrick de Vos. As I said, today we are going to talk about milling strategies together with my colleagues. Viju from India, Alesia from Italy, and we have a new face, a new team member. Margarita from Germany is today also here, and these 3 people make it possible that this happens. I have the fun part, I can talk about milling and stuff. These 3 people have the difficult part, making it all happening, making it all possible. What is a milling strategy? What is a strategy? And perhaps I should give you the example. Imagine that you are moving and you have to move boxes. Imagine you have to move 3 boxes. One could start talking about a strategy then, how to move boxes. If you are strong, you could take all 3 boxes at the same time, make one movement from point A to point B, and that's it. Job done. An alternative strategy, if you are not so strong, could be that you take box by box and you move 3 times from point A to point B. And perhaps you are fast and you run from point A to point B. Could be a second strategy to move 3 boxes. The third strategy could be, if you are not strong, if you are not fast, perhaps you are tall and you can take big steps to move from point A to point B. That could be a third strategy. So strategies, and also milling strategies more in particular, is about a scenario on how to do things. And if we talk about strategies, there's always, I have heard it 1,000,000 times that people ask me the question, what is the best milling strategy? Now, it's a good question, it's a fair question to ask, but it's impossible to answer if you don't know the for what. What is the best milling strategy for what? It could be a technical thing. What is the best milling strategy to produce a tin wall? What is the best strategy to do face milling in titanium? What is the best strategy to do economic milling? So the question, what is the best strategy, is only answerable if we know the target. Every discussion on a strategy, every discussion on a milling strategy in particular, should start with, what is your target? What do you want to achieve? What is important for you? What is your priority? And then, if that is known, then we can start talking about a milling strategy as being a scenario for a single milling operation or for a combination of milling operations to finish a workpiece, but what is the scenario you should follow to achieve your target? That is what we refer to as a milling strategy then. And if we talk about milling strategies, we have some variables in the equation. A milling strategy is about which milling cutter type are you going to use. It's about how are you going to handle the operation conditions. It's about which cutting data should you use. It's about the movement you have to give to the milling cutter, the tool path you want to have during the operation. That are the things we talk about when we talk about milling strategies. And talking, I'm a bit, how to say, I'm polite here if I say talking, because very often when it's about milling strategies, it's about discussing. And a very important question in this thing is, who leads the discussion? Where does it start? It starts here to the left, always. That's fixed. We cannot discuss milling strategies if we don't know the target, if we don't know what we want to achieve. But afterwards, how things connect to each other, yeah, there are different possibilities here. You can start with the toolpad, as you see on the picture right now. You can start with the toolpad, and that leads to machining conditions, that lead to the cutting edge type, and that leads to the cutting data. Could be one approach, but there are much more typical approaches. And to keep it simple, if we say, if I look to a milling strategy, who leads the discussion? Who drives the discussion? Who is important? One could say, is it CAM, which is in these time and ages very often it all starts with CAM and a program and the programmers and are they the ones that should take the lead here and say, okay, we have a milling cutter and we want to move it like this and this and this through a workpiece, and in doing that we generate a correctly finished surface, a machine surface, a workpiece? Could be, but bear in mind that for CAM, the picture you see right now on the screen, that's a milling cutter. It's a cylindrical piece of carbide or whatever cutting material with a certain length and with a certain diameter, and that's it. And another group that could lead the discussion is the technological approach, the milling cutter. Does the milling cutter takes the lead? Is it okay? I have here a certain tool, certain milling cutter with certain features, with certain properties, a diameter, number of teeth, a geometry, whatever, and I want to use that to the best of its possibilities, and CAM has to follow. CAM has to make sure that this cutter moves in a workpiece in such a way that we maximize the possibilities we have of the tool. Could be another approach. Here we have to bear in mind, however, that not every movement we would like to give to the milling cutter to maximize its performance is possible. But anyway, what do you think? Based on your experience, and put it in comments here, what do you think? Should CAM lead the discussion? Is it the tool part comes first and the milling cutter comes second? That would be option A. Or do you think, no, it's the way around it? The milling cutter comes first and the tool part needs to be generated as such that I maximize the possibilities of the cutter. What do you think? Well, interesting for me to know and to see afterwards how the opinions are on this, because this is a discussion I have been in since 30 years, I think. And I think it's never going to end, but anyway, it's an important discussion. Now, why do we need milling strategies? We know what it is. We kind of defined what a strategy is about. It's about a scenario Why do we need to discuss about them? Why didn't we discuss those things so intensively 30 years ago or 40 years ago? Why is it always on the table now? Well, we need milling strategies because more than ever before, and what you see here is a picture showing beyond technicalities, because of course I want a milling operation with no problems. I want a workpiece which is correctly finished. All of that goes beyond saying. But next, on a next level, we can ask more things from a milling operation, and then we are more into the economical side. We can put demands on costs, we can put demands on productivity, we can put demands on energy efficiency, all those things that comes next, that comes beyond the pure technicalities, that those are very much in the picture now. And if I look to milling as an operation, now, to do something technical, to arrive at a correctly finished surface, machine surface with all the specifications respected, there are a million methods we can figure out. But if you go one level higher in the discussion, and if you say, yeah, but next to technicalities, there are also the more economical, the more sustainability thinking elements we have to bring into the picture, that's the moment we will have to make comparisons. That's the moment where we say, okay, I have here 3, 4, 5 systems, strategies. Which one brings me closest to the overall wanted target, being a correctly finished machine surface, a correctly finished workpiece, but also responding, also in line with specifications that go beyond the pure technical specifications. And that's why at previous sessions, we spent 2 sessions on basically the picture you see here. Because having a milling strategy discussion, or having a machining discussion in general, kind of one, I could say, it cannot be done without taking into account these things. We need machining strategies, we need milling strategies, because we are confronted with economical demands on the operation, much more than it was in the past. And that's why we need to work with that. And working with milling strategies, a milling strategy is about a scenario. It's the scenario we need to make sure that the operation leads to the technical wanted result, a correctly finished workpiece, but also beyond that, it leads to the economical wanted result, being it whatever is your priority, cost, productivity, efficiency, resource efficiency, energy efficiency, whatever. And how do we work then with strategies? How do we work with that? Well, a milling strategy, first of all, we have to realize that there is always a starting point, and the starting point is your target, is your goal, is your priority. As I already said a couple of minutes ago, what's the best strategy is a question that can only be answered if we know the best strategy to achieve what. That is very important. Without that, we are helpless. So there it starts. Next, milling strategies is about defining equipment to achieve the goals. And equipment is the machine tool, the milling cutter, the tool part selection, whatever. And thirdly, it's about, okay, if I have now defined my equipment, how am I going to use the equipment? And that is more practical, more concrete. That's the moment we start talking about cutting methods and cutting data and all that type of stuff. And in that discussion, there are different, as I already said, there are different focus points, different points where we can start from. If we talk about the overall target, that's the moment we talk about, one could call it sustainability strategies. I don't know if that is a correct wording of it, but it's your overall target. It's about economical thinking, productivity, reliability, that type of thing. We also will have to have a discussion, a talk about what is referred to as geometrical strategies. And geometrical strategies is basically, how do I move a milling cutter? How do I move a tool? Linear, circular, trochoidal, whatever. There are multiple possibilities there. We could take the focus point of that. We say, okay, no, we start with the tool and the application strategy, the tool type and the application strategy. That's the moment we talk about face milling cutters and end mills and disc mills and all that type of things. And finally, the subject of the next session, technological strategies. Personally, but I emphasize personally, and yeah, in all the discussions, I'm very open for other opinions, of course. But personally, I think technological strategies are where everything comes together. Kind of technological strategies is if you look to a cutter with certain features, properties, and if you see the type of tool part you are thinking on generating, how to make sure that the milling cutter you are thinking on and the tool part you are thinking on, that the two can reinforce each other, work together to come to a better result. Technological strategies is the moment we start talking about high-speed milling, high-feed milling, high RPM milling, all that type of slogans. So what I mean with focus points is a bit connected to what I said a couple of minutes ago. Where do you start? What is your opinion? Should I start from the tool part and then make sure that all the others follow and are in line, or do you start from the milling cutter and you go from there on? It's and there's no rule here. I cannot give you a formula, kind of A plus B equals C or something like that. It's very much depending on personal preferences. And these elements and these variables we use in those focus points, it's one could say, first of all, we have to bear in mind, we have to respect the reality in which we are going to perform the operation. A reality is the machine tool. And I consider a machine tool a reality in such a way that a machine tool mostly is a given thing. You have a milling machine and that's it. It's not like with milling cutters, that you change every 10 minutes. You think, oh no, I don't do this, I go for that. A milling machine is a given thing. And a milling machine has features, has possibilities, has limitations. And whatever approach we select, we will have to work within what is possible with the machine tool. The same goes for the application environment. Do we use cooling? Don't we use cooling? Is it high pressure cooling? Is it normal cooling? But what is the global tool concept we are thinking on? All of those things which are basically about the environment on the machine tool, we also need to take into consideration. It's also going to give us possibilities, but also constraints we have to realize. And the workpiece geometry and how a workpiece is fixtured. The surface we need to machine, how is it accessible? The global tool concept, what dimensions of tools are needed to reach out to where we need to do the operation? How sensitive is the workpiece as such for instabilities, vibrations, and that type of things? And if I can give you some examples of things you have to be aware of. An example for a machine tool. Basically a machine tool, and it's a setting you can change in the numerical controller of the machine, but you can make a machine tool move so she respects speeds, movements, or you can use a machine tool as such that she respects accuracy, tolerances. But if you say to the machine, whatever movement I want, whatever speed I want, the feed speed, for instance, you have to respect what I tell you to do. That means that there will be, as the faster you want to move the tables on the machine, there will be a loss of accuracy. Speed goes at the expense of accuracy. How much? Yeah, that's depending on the type of machine tool you use. That's depending on the type of milling machine, the condition in which she is, whatever. It's you want something and it comes with a price. You can, what you see here to the right, that's the other option to use a machine tool where you say, okay, uh, accuracy is important. I talk here about a finishing operation. I need accuracy. Well, if you need accuracy, then a machine tool is going to modify the speeds with which she moves. Accuracy comes at the expense of speed. And it's something you have to know from your machine tool. How does she react? How do you steer the machine tool? Because the consequences afterwards, if you think the milling cutter was moving with a table feet of 6 meters per minute, but in reality the machine tool decided to reduce it to 4 meters per minute due to that accuracy was important, yeah, that means that the milling cutter is going to be used with cutting conditions which are not the correct ones. And the milling cutter is going to behave accordingly. So you must be aware of these things. Conditions. I use here 4 photos to illustrate the 4 seasons in a year. If you have the same situation, but if the environment is different, that will create a situation which is for the tool you use different. Yeah, you must be aware of that. Because if you do all your preparation, if you do all your production engineering work, and you consider that the machining is going to be done with high pressure cooling, but for some reason at the machine tool itself, due to I don't know what else, but there is no high pressure cooling. That has consequences. So the environment in which you do machining must be known and must be respected. And a third example I can give you is when you look to a workpiece, in milling there is a rule of thumb that says you should always use the best milling cutter possible. And best is defined when we talk about dimensions as a short milling cutter, short clamped in the spindle, and a big diameter. That's the ideal milling cutter. However, if your workpiece has a geometry that does not allow that, and you can't use the milling cutter as illustrated here to the left in the picture, but for reasons of accessibility, you need to use a long milling cutter with a small diameter. It's a necessity. You cannot change it. And that, of course, will influence all the other selections you do. So, working window is about which machine tool do you have? What are the possibilities? What are the strong points? What are the weak points? What is the environment in which you are going to do the operation? Is it favorable? Is it unfavorable? What are the limiting factors you have to bear in mind? And it's about the workpiece itself. Does the workpiece, the geometry, the form of a workpiece, the dimensions of a workpiece, does it allow you to go for a global tool concept which is favorable, which is good, or are you necessarily wise restricted to a tool which conceptual is not so ideal to use? CAM. Everybody talks very generic in CAM. They say the CAM system. Now, years ago, I did a test once, and I took a number of CAM systems, instructed each system to select what the system itself thought to be the best approach to do something, and gave each time the same mission, the same workpiece to produce. Well, the result of it, you see here in the graph to the left, every CAM system came with a different solution. So what I try to say here is CAM systems are like milling cutters. There are different types of milling cutters. There are different types of machine tools, but there are also different types of CAM systems. So if you talk about CAM, be careful. which how to say, which brand, what's the philosophy which is built into the CAM system? How does a CAM system looks at the operation? All very important things you need to know as a user. Milling cutter type, milling cutter features. Uh, Also here, there are dozens of features that needs to be selected to come to a milling cutter that you use. Also here again, I don't think today there exist bad milling cutters anymore. But what I do still believe in is that there are badly selected milling cutters to do a certain job. So give it the needed attention. Cutting conditions, cutting data is a chapter on its own. And by the way, I started to talk about dynamic milling. I want to spend a couple of minutes here again on dynamic milling. Cutting conditions. First of all, if we talk about cutting conditions, be careful how you define them, because today we talk not only about linear milling, but we have also non-linear milling operations. And we normally, traditionally, we talk about milling cutters with straight cutting edges, where I would not say the majority, but a big amount of milling cutters today is with non-straight cutting edges, with curved cutting edges. And these are two things that we need to take into consideration when we talk on a higher level about cutting conditions. Do we talk about straight cutting edges or curved cutting edges? And do we talk about linear milling or non-linear milling? Are two important things to consider. And if we think on a philosophy to work with cutting data, there are two very, very distinctly defined approaches. One is referred to as the static unified approach, where you, for once and for all, kind of select cutting conditions for a milling cutter in a certain application, and that's it. Or you go for dynamic modified. Dynamic modified means that at each moment in time, you look to the reality with which a milling cutter is confronted. And the picture here to the right, I give you an illustration. If you have, in this case, non-linear milling, it's copy milling, and it's combined with round cutting edges. In such a case, if a milling cutter is moving over the surface it needs to generate, it means that the effective cutting diameter is constantly changing. Well, dynamic modified cutting conditions means that or the CAM system or the machine controller or both recognize that every second the reality for the milling cutter is changing and modifies cutting conditions accordingly. That is dynamic modified cutting condition selection. And the definition, and yeah, as I said, dynamic milling, is it a strategy? I don't think dynamic milling is a strategy. I do think dynamic milling is a method to work with cutting conditions. It's a choice you make. And if we talk about cutting conditions, also very important to know the correct definitions of cutting conditions. Because you see here an animation where I have a milling cutter, and the milling cutter is cutting along a straight line and then comes into a corner. And that means, I give here the example of radial depth of cut. Radial depth of cut is the width over which a milling cutter is in contact with material, measured parallel to the radius line of a milling cutter. But that means when a milling cutter comes in the corner, suddenly it's confronted with a different radial cutting depth. That means in one operation you have one tool, one milling cutter, that depending on where it is in the operation is confronted with one of the cutting conditions, the radial depth of cut, which is modified. By the way, you know the consequence of this, that the milling cutter starts vibrating in the corner, which makes very, very much sense because, yeah, the loads acting on a milling cutter are suddenly completely different. But how do you work with that? How do you avoid that a milling cutter is vibrating in the corner? put your suggestions in the comments here. I'm looking very much forward to see what you give there as comments, because it's daily reality. This that milling cutters are confronted with suddenly modified situations under which they are used, and that influences, of course, the behaving of a milling cutter. What is the feat? I always, you see the pictures here. You know, these pictures are, I think, 35 years old. So old is this discussion about the feet. What is the feet of a milling cutter? You see here circular milling. It should not always be linear milling, but circular milling. And you see two possibilities for feet. You put the feet with which you use the milling cutter in the center of the milling cutter, which is situation C. Or you put the feet on the periphery of the milling cutter, which is situation P here, the situation to the right. Now, which one do you think is correct? Which one do you think is good? Situation C, I put the feet in the center of the milling cutter, the center line. Of situation P, I put the feet on the periphery of the milling cutter. Put it in comments. I'm very interested to see what your opinion is on this. Compare it with linear milling, because it's one of those things people do not think about really, because forever it was, yeah. If milling is a situation where you have a circle and you move it over a certain distance, which is referred to as the feet per tooth or feet per rotation or feet per minute, whatever, the feet, which is the movement of a milling cutter over or in a workpiece. In case of linear milling, periphery or center, it's all the same, you know. You move a circle over a certain distance and that's it. Every point on the circle is moved over the same distance. But in circular milling, that's not the case. So which one is correct? And you know what? I'm not going to give you an answer here, because this is a major subject for the next event we have, where we are going to talk about technological things around milling strategies. And a very important point there is just this question. What should it be and what is correct? Now, if you work with these things, as I already said, that is the difference between static unified, I have one milling cutter, I have one set of cutting conditions, that's it. Dynamic approaches, and dynamic, basically the word that should be used is variable. Variable approaches is where I take into consideration that a milling cutter situation, second by second, can end up in a different situation that leads to different behavior of a milling cutter, and I want to compensate for that. And that brings me to a little group of strategies, very often overlooked, not given enough attention to, but it's referred to as entry strategies. How do I start an operation? How do I start a milling operation? And you see here an animation that gives me two very different situations to start up a milling operation. The one to the left is referred to as radial in-feed. The one to the right is referred to as tangential in-feed methods. It has all to do with recognizing that cutting conditions modify during or potentially modify during an operation, and that we compensate for that. And just a few words on compensation principles in milling. I take the example, which is very simple to understand, but next time I'm going to work with more than just one example. What you see here to the left is slot milling. You take 2 times the same milling cutter and you use it in a slot milling operation, where to the right you see an operation where the milling cutter is used in side milling or contour milling. It means that the angle over which the milling cutter is in contact with material, in case of slot milling, is rather high, in case of contour milling is rather small. That means that, for instance, if I look to the temperature in a cutting edge, in case of slot milling, the temperature is going up rather fast. A cutting edge is cutting, not cutting, cutting, not cutting, but the part it's cutting is rather big, so rather fast a temperature in a variable way goes up. In case of side milling, contour milling, the same phenomena takes place. A cutting edge, the heat in the cutting edge is building up, but much slower, because the part where heat is generated, the part where a cutting edge is in cut, is rather small compared to the part where a cutting edge is not cutting and cooling down. That means if I look to a cutting edge, and if I do realize that temperatures in cutting edges, there is a zone, there is a window in which those temperatures should be. I think everybody can feel by sentiment that the temperature should not be too high, or you burn your cutting edges, and that leads to very short tool life. So there is somewhere a critical maximum temperature, but you have to realize also that there is a critical minimum temperature. A cutting edge needs a certain minimum temperature to have toughness. And if you want to practically understand what I talk about, take whatever milling cutter, take a hammer and give a very short knock on a cutting point. You break it. And the reason you break it is because the temperature is low, too low. And that makes carbide or whatever cutting material we use today rather fragile. And fragile means it breaks. So if you don't reach a minimum critical temperature, you also are going to suffer from short tool life. So it's all about having the temperature in the correct zone. In case of slot milling, or in case of situations where a big part of a milling cutter is in cut, it's going to be mainly worrying about too high temperatures. We have to limit the temperatures. In case of contour milling, side milling, it's just the opposite. It's more about what can I do to increase the temperatures, to lift it as quickly as possible above the minimum temperature I need to give the cutting edge toughness. Now, if you work with that, and if you are aware of that heat is in cutting, in machining, generated by cutting speeds. Cutting speed, kind of, one could say, is the generator in the heat generator, is the fuel in the heat generator machining is. That means that high cutting speeds give high heat generation, low cutting speeds give low heat generation. High heat generation leads to higher temperatures, and low heat generation, lower temperatures. But with other words, it means that related to the part of a cutting edge, part of a milling cutter in contact with workpiece material, compared to the part where there is no cutting, so no heat generation, and that relation is given on the horizontal axis here, percentage-wise, it's the relation of radial depth compared to the diameter of a milling cutter, the so-called AE divided by D, the AED ratio. To the right, it's 100%. To the left, it's approaching 0. And the vertical line, the vertical axis, is cutting speed. If you have smaller parts of milling cutters, radial depth of cut, in contact, you need to increase your cutting speeds. If you have bigger radial depths, then you need to reduce your cutting speed. All of that to keep your temperatures in the correct zone. The moment you start working, thinking like that, that is referred to as compensation principles in milling, compensation principles in machining in general. But also that part, I go rather fast here, and it deserves more attention. Compensation principles. But the next event, we are going to spend quite some time on compensation principles in milling, and how can we work with it, and how can we take advantage of those things. But here I just wanted to define for you what is meant with it. Dynamic milling is where I apply actively compensation principles in milling. That is how it all relates to each other. Now, I write here a kind of a conclusion, because after one session, it's not really possible to come up with a conclusion. As I said, this is the first of a series of 4 sessions we plan on milling strategies and milling techniques. But as a kind of a conclusion, one could say we have a dilemma. The dilemma is I have situation A, which is a raw workpiece, and I want to end up in situation B, which is a finished, correctly finished workpiece. And beyond that, I also have some demands, I also have some targets on sustainable stuff. Cost savings, time savings, productivity, cost efficiency, energy, whatever, the beyond the pure machining. How to go from A to B? Yeah, there are lots of ways. And that's just what it's about when we talk about strategies. Which one should we prefer? Which one most probably will lead in the most efficient and effective way to the wanted result? There's always, and that is a discussion, and I don't think the discussion will end today, but there is always kind of I refer to it as the geometrical approach. And that's a little bit, I call it the GPS approach. It's like you in your car, you are in point A, you want to go to point B, and you ask the GPS on your mobile phone or in the car, how do I do that? And then the thing will give you the road. Go straight, turn left, turn right, whatever. That's one approach. This approach, however, does not take into consideration the type of car you have and how good a driver you are. This is just geometry. That's the other thing. Another solution is that you start by saying, okay, I have this type of car, and I can run this speed, and it has this acceleration, and the car and the features. I talk here about the milling cutter. And I have a driver. The programmer, the operator, somebody driving the car. That's another approach. This approach, perhaps the thing gives you the shortest possible way, but you need to drive a bicycle because you are going to enter narrow streets. But it's not given here. Another approach is, wait a second, I have here a supercar, I can do miracles with it, and on top of it, I have here the best driver in the world. Find me a way where I can fully exploit the possibilities of the car and the driver. Of course, the smart approach is if you can bring the two together. But that's why I said it's kind of a solution, because it's not yet defined. Still not. Who decides first? Is it the tool, the equipment, the user of the equipment, the engineer, the operator, and the geometry has to follow? Or is it the geometry that decides, and it's up to the operator, the engineer, to figure out what is the best way, the best tool, the best cutting conditions to follow this road? But as I said, the two together, if the two communicate, if the two act together, that's the moment, we find a champion solution. And that's a bit, where I wanted to come today. We need milling strategies because beyond technical stuff, for which there are thousands of possibilities how to achieve technical, the finished product, the finished workpiece. But beyond it, and by day it's getting more important, the sustainability layer, economics, productivity, that type of thing. And then suddenly we need a method, we need a strategy, we need a scenario to figure out of the thousands of technical possibilities, which one would suit us best. That's why we need them. It's about scenarios. It's about deciding which road, which tool, which cutting conditions. That is what we need to do when we talk about milling. And working with it is were not always easy, because it's sometimes, one could say, a bit of a fight between priorities. Who drives the discussion? Who has the biggest voice in the discussion? And yeah, that's not yet decided. I hope it was an interesting 45 minutes, 46 minutes by now, I should say. Let me check before we end this up, what questions we. It's always lots of questions when we talk about strategies in machining. Let's see how many of them we can answer today in the time we have. All the others, the questions I cannot answer, I promise you afterwards in the comments where the question is, I try to give you the best possible answer there also. Would you... One, I don't know if it's a question, but anyway, I read it out loud. Would you think of strategy as the way to do the job? Yes. Selecting different ways to use a tool, indeed, that's part of the whole discussion. You could use plunge or trochoidal milling. Yeah, there are options to do things. Is it a matter on how it will get worn? Yeah, that's the sustainability layer. So the question from Antonio, which basically is not a question, he makes a number of statements, and I agree with every statement. You put in a couple of sentences the core of this presentation together. There is a question also, what kind of strategy to be followed for achieving better flatness in a thin-walled aluminium die-cast part? Yeah, now I'm going to be a little bit political. In machining, in milling, there exists, but next time here I'm going to use it as an example. There exists a strategy which is referred to as thin wall machining, thin wall milling, which is a combination of geometry and technology. And the question is from Arafind, can you give me some more time next time in such an event as today? I'm going to talk about it. Otherwise, in the comment, I can give you already some more information on what is referred to as thin wall milling. And next question. The block speed processing of the control has a huge effect on accuracy at high speeds. A very correct statement from Frank. Most people are not aware of that. I also agree with that statement. Frank, we are on the same line, on the same level here. As I said, the machine tool you use indeed can give you possibilities, but also gives you constraints. The block speed processing, and you know that's why over time there have been developed different approaches for that. There is something called NERP programming, where we try to make it possible to machine at extremely high speeds, and that block speed, the processing of it, is not a limit, or is lesser a limiting factor. But a very correct statement. But then I see that Osman has a different point of view, but I do not understand from the question a different point of view on what. It's more appropriate to call the answer to the hybrid, because manufacturing methods may vary in small. Here you put your finger on something very important. That is, the batch size in the whole discussion. Are we going to produce big batches or small batches, smaller batches? because machining is part of the picture. The machining time is part of the picture, but beyond pure machining time, you have other things also. And if we discuss about productivity beyond pure machining productivity, but a real production productivity, we have to be aware of that. And then indeed, as Osman says here, the way of working, how to select a tool, how to select cutting conditions, which tool path to generate, how to relate things to each other, will be influenced by the batch size. I fully agree with Osman that if you take one workpiece, and if you say I have to produce 3 pieces of it, or if you say I have to produce 3,000 pieces out of it, I also will come up with a different approach, very clearly. So yes, Osman, I fully agree with your different point of view. Although I do not still understand different point of view about what, but put it in the comments. We can continue the discussion later. The next question is, wait, let me pre-read it a bit, because it's also a long, no. A question from Akash: do I have study materials on these principles? Yes. There's quite some materials available. If you leave some information in the comment, we see later how I can make sure you have them later on. The 6th question: is coolant water better than coolant oil? Sometimes not. This is such an open question. I cannot give you a simple yes or no. This is a subject perhaps we should take on a next session about cooling systems. The next question is a question about if I can give some comments on static testing of harmonic variables regarding the machine type tool holding, the tool and material being machined. Yes, I can give some comment, but not in 1 minute. Because here you are very correct, or I think I understand the background to this question, and that is very often in machining, we do testing in static defined situations, and then we kind of generalize it, and we neglect the fact that machining, milling in particular, is a dynamic process, dynamic defined in a way that the conditions under which the cutting edge are cutting is constantly changing. That leads to different behavior, that leads to different physical phenomena happening during the process, and that means that those those what is referred to in the question here as the harmonic variables, they are very often overcoming or being more important than the static variables in the equation. So I don't know if this counts as a comment. As I said, this is a huge subject you are touching here upon. But I would one comment I could give is if it's really important for you to fully be in charge of the machining process, I mean that you fully control what's going on. Static testing is not good enough. You have to do the measuring, the testing in real life, and real life means that in machining and in milling in particular, harmonic variables in the equation are too big, too important to neglect. So you have to know about them. I still have time. The next question: tool geometries are equally important when dynamic. Yeah, of course. When we talk about dynamic milling, as far as I understand it starts with a statement that geometry when we talk about dynamic milling is important, yes, of course it's important. Uh, Dynamic milling, I would say, and dynamic milling, my definition of it, remember what I said, dynamic milling is a situation where I do realize that the conditions in which a milling cutter is functioning is changing in time, and cutting conditions should be modified to compensate for that, my compensation principle. I think geometry is variable number one in those things. The example I gave you was the radial depth of cut and the diameter of a milling cutter, and how the ratio is between those two. And then comes the question, my interpretation, it's a question that more information on tool mechanics with respect to milling strategies would be very helpful. Indeed, there I would refer to the technical literature we have. You know, in SECO we have 4 or 5 books on machining. And therein you find quite a lot of information on the different physical phenomena that are going on during machining processes, and how that interact with the tool and the workpiece and so on. Still some time left. How do I see milling technology in the next 10 years? I don't know. But what I can say, what I can tell you is how I would like to see it. And I go back to my kind of a conclusion. Because, you know, I said one approach to find the best way of doing things is the geometrical approach, the GPS approach. I said another possibility is that you talk about the tool, the car, and the driver, the engineer, the operator. And if you start to combine those two, you end up with millions of possibilities. And today we are in a situation where evaluating all those millions of possibilities is just impossible. We very often we take a decision based on gut feeling, you know. I think this will be the best, so let's go for it. Especially in small batch machining, as one of the people made a remark about. Well, what I hope to see happening in the future is, because I hear people talking about artificial intelligence all the time and digital machining. Well, what I hope is that impossibility to evaluate every possible combination can be done in a should I call it a more scientific way instead of a more gut feeling approach. That's what I would like to see. So I think the more we are in the possibility to really evaluate everything in a fast and a smart way, that will lift milling to the next level. I don't think it's going to be about new milling cutters and new carbide grades and better CAM system. I think it's going to be in a more intelligent approach. Hopefully, artificial intelligence approaches, digital approaches will help us with that. If that will happen, I don't know, but that's what I would like to see. And then the questions continue to come in. Sorry, the time. One last question. A question from Dirui. How do we overcome a situation when we have to machine different materials at the same time, like very hard cast steel and soft steel in an assembly? Yeah, that's the moment you have to start thinking on averaging your approach. And here perhaps it's a bit related to the previous remark also. How do I see milling in the future? Here it's about Today we count on expertise, we count on experience. We say, okay, I have a look at the situation. My estimation is not really based on something, but it's just a feeling that the hard material is the one that is going to give. I give an example that the hard material is going to give the biggest issues during machining, so I focus on that. And that I come to a situation and an approach which is not ideal for the soft material, yeah, okay, I live with that, or vice versa. Situations like that, there is never ever a best solution. It's always in average a best solution, but hopefully we can, in the future come, faster to, based on, let me call it, scientific approaches, solutions. I really want to stop here because the time is up. Today was very generic milling strategies. Why do we need them? We need them due to the things beyond pure technical stuff. What are milling strategies? It are scenarios on how to combine different elements. And that's how we work with milling strategies. It's all about, I have to select a tool, I have to select cutting conditions, I have to select a tool path. How do I come to the best possible solution in a given environment on a given machine tool? The next session on the 19th of December, we are going to focus on what I think personal is perhaps the intelligent approach, because it combines. It's the technological approach. What do we do? What are technological milling strategies? And how should you use them in the best possible way to take full advantage of them? That's the next session we plan for the 19th of December. I hope to see you there. There were quite a lot of questions I didn't have time to answer, but the coming days I put in comments all the answers possible. For those who ask for more information about things, leave some of your information behind in the comments. I contact you later and see what I can send you or can help you with. Anyway, I refer for a lot of reference material in the technical books we have, where you find quite a lot of material already. Thank you very much. I hope it was an interesting hour, and I'm looking forward to see you within a little bit less than a month. Thank you very much on behalf of my 3 colleagues and myself. Bye-bye.